Hello, we are going to talk about Linux containers and specifically about LXC, Docker, and how these technologies are changing how IT works and operates. My name is Simone Brunozzi, and you can find me on Twitter with the handle Simon. This is the agenda. We talk about what are containers and why people are interested in containers, a quick introduction to LXC, a longer introduction to Docker. Then we're going to see how Docker is used in the real world, and then some conclusions at the end. So what are containers? This is a concept that have existed for more than 10 years in IT. It started with BSD jails, and then it was applied to Solaris zones and AIX, WPAR, while Linux containers, also called LXC, were created by Google engineers in 2008. In essence, they are a set of processes that runs on top of a kernel that they share and essentially leverages user space interface to use containment features that are provided by Linux kernel from version 3.8 onwards through APIs and tools. Another way to describe it is an OS level virtualization. So it's virtualization that happens at the OS level instead of happening at the underlying hardware level, which is the most well-known form of virtualization today. Why containers are so interesting? Well, they theoretically allow you to run your apps everywhere because those apps become portable. They allow for rapid provisioning. They separate concerns between developers and ops, or people in charge of operations. They assumedly are better for web infrastructure type of IT needs. And given that they are very popular, that's a good reason to explore them. There's also a long discussion about containers versus VMs, and we're not going to talk about it here. However, just a word of warning, containers in the real world are not as nice as they seem on paper. So there is some caveats that apply. First steps with Docker. Here are some first steps with Docker, which is a tool that automates the deployment of applications inside containers. I have installed boot to Docker on my machine and initialized it. And you can replicate those simple steps in just a few minutes. Or you can use Kitematic, which is a high-level, nice app that allows you to interact with Docker containers. Let me show you how things work very quickly. This is my bash. I'm looking at the Docker version. It means that Docker runs and operates. I look at the processes. There is currently no process running, so no container running. So let's launch one. The command is run. T is TTY, I is interactive. I'm going to base it off an Ubuntu machine, and I need a bash. And here I am. I'm inside a container now. It's isolated from the rest of the operating system. And I can see that the number of packages in this container, 189, it's lower than the more or less 500 that you find in a traditional vanilla Ubuntu machine. And after I exit, that container no longer works, that container no longer runs. But I can run it as a daemon with the -d option. In this case, I want it to ping the Google DNS 8888 forever. And once I do that and I run docker ps, I can see that there is a Docker container running with the name determined pasteur. This name is generated randomly. And then I can log into that container by using docker exec and bash. And now I'm inside it. And in fact, if I look at the process trees of this machine, I can see that there is indeed a ping running on Google's DNS. I can exit from this machine, and then once I'm done, since I don't want to let this run forever, I can just use docker stop and then the name of the container, and that's it. Or the ID of the container if I want to. So here's a first very quick example of how Docker works. So a few considerations. As you saw, containers boot in fraction of a second. They can be stopped or killed in a very short time. Very important, they use the same kernel as the host operating system. They provide a form of isolation They use it. They use something called user namespacing to offer that. And as you saw, they can run as a daemon, so you can leave them running for a long time. Resources and resource allocation, so CPU, RAM, disk I/O, network, are handled with something called C groups that allow you to meter, limit, reserve capacity within an operating system. Now let's go back to LXC for a few more slides, and let's introduce LXC. So LXC, also called Linux containers, is a virtualization environment at the operating system level that allows you to run isolated containers on a single Linux host or a control host. And it consists of tools, templates, libraries, and some language bindings. It's very low level, very flexible, and allows you to use pretty much every containment feature that is supported by the kernel that you are using. And kernel namespaces are the things that provide isolation of process trees, networking, user IDs, and file systems that you have mounted on that machine. LXC, however, has been created by Google engineers in 2006 with the primary goal of better resource management within the same machine. This is a quote from someone that was recounting that experience. A server with containerized guests could establish two top-level containers to control the usage of CPU time. Guests could have 90%, but the system tasks will still always get at least 10%. The way, for example, the mail will continue to be delivered regardless of what the guests are doing. So as you can see, they've been created with a different purpose in mind compared to what people want to use them for today. So LXC, in a sense, is something between chroot and a full-fledged virtual machine. chroot is a command that changes the apparent root directory for the process that you're currently running and its children. So the process is jailed within that chroot, so it can't see outside it, and it provides privilege separation and other things. So LXC sits in between a chroot and a full-fledged VM. It has, in fact, differently from chroot, its own process and network space using Linux kernel C groups. Those are some example commands that you can run with LXC. You can create LXC with LXC-create using a template and giving it a name. You can list the LXCs, the containers that you have. You can start them. You can get info about them. You can log into them. You can freeze, unfreeze them, clone them, stop them, destroy them, etc. The syntax is pretty self-explanatory. LXC, however, is not widely popular. It's relatively complex to use properly. This is something that Docker solved. It is not designed with security in mind. You saw before that it has been designed primarily for resource allocation within the same machine, and there is a lack of industry tooling. There's also some related projects. LXD, which is a hypervisor, very similar to OpenStack Nova. CG Manager, it's a daemon to manage C groups, and a user space fuse file system called LXCFS. And in terms of security in general is a concern. It can be improved by running processes as a non-privileged user, or simply getting rid of SUID binaries or mount with no SUID. And also, since LXC version 1.0, which was released in February 2014, you can run unprivileged LXC containers. So they don't have root privileges, and therefore they can't do much to damage the host system. However, LXC is still vulnerable to buggy system calls, which you can limit with seccomp, and that's a relatively complicated effort. Let's talk about Docker now. What Docker is not, it is not a virtualization tool like VMware or VirtualBox. It is not a configuration manager like Chef, Ansible, Puppet. It is not a VM manager like Vagrant. It is not LXC, of course, even though it leverages LXC in the backend. Let me give you a short digression here. Tar and Deb. Tar, as you know, is an archiving tool is a software utility that allows you to package stuff together. Deb or Debian packages are standard Unix R archives that include two optionally compressed tar archives. One is the one that holds the control information. The other one contains the program data. And dpkg is the tool that you use to handle their packages, which are properly built and maintained by maintainers. Deb vastly simplifies what Linux users were accustomed to do with tar. And in fact, I would say that either Deb or RPMs are now by far the most popular way to handle software packages in Linux. That digression was important because tar is to Deb what LXC is to Docker. So Docker, as I told you before, is a tool that automates app deployment, but very importantly, it vastly simplifies the use of LXC. So very similar to what happened to tar archives with the packages. In a way, Docker has commoditized LXC. There's also another way to look at it. Docker might do to APT what APT did to tar. APT apt-get is the tool that commonly used in Debian-like Linux distributions to manage software packages. apt-get install name of the package, and of course apt is an example of how the benefits of having the data and the metadata with it together allows for a better maintenance of your software packages. So Docker might do the same to apt as well. It might actually provide a better way to handle software packages. Docker uses the libcontainer library to directly use virtualization facilities provided by the Linux kernel, and in addition to indirectly through LXC. And it also offers high-level API for every operation. Those are some of the Docker features. It's written in Go, it runs as a daemon, comes with a command line interface, of course, and exposes everything through a REST API. You can build and share images through registries, and then from these images you can launch a container. And those containers have a standard format. They use layers. Every layer is the tarball and the metadata, and you can stack one layer on top of the other, very much like containers. And that, of course, allows you to reuse a specific image to create a new image that is more specialized. And it offers a standard way to easily build trusted images using Dockerfile and StackBrew. And there's also Docker Hub, which allows you to host registries in public for free or have private ones, in which case you need to pay. Those are the advantages that Docker claims to have over LXC. It's portable across machines because it uses a standard image format. It's focused on the application, not on just making a machine more lightweight. It allows you to build automatically. It provides versioning. It allows you to reuse components. As I told you before, you can use multiple layers. So you create a base image and then you add on top of that. So you add a layer, allows you to share those images through a registry. And it provides an ecosystem of tools around it. In theory, this is the best of both worlds. Usually you had to compromise between minimum overhead but less portable versus more portable like a full VM but a lot of overhead. And configuration management tools are something in the middle like Puppet, Chef, Ansible. But in theory, Docker gives you almost the same portability as a VM, even though it's only Linux, even though you need to use the same kernel for all containers on the same host, but with much less overhead. So this is the theory of Docker. Then we're going to see how it works in practice. This is an example of deployment without Docker. You have your machine on the left. You have a virtual machine running there. That virtual machine should be the same as the staging and production server. You see them in yellow color. So you create a project code and then a provisioning script. Then you apply them to your virtual machine. If they run properly, then you push them into GitHub or another repository. And then from GitHub, that code is sent to the staging server and later to the production server using those provisioning scripts. So this is very important in this case. Those three environments, the virtual machine in your own machine, the staging and production servers should be the same. In the case of Docker, deployment changes dramatically. You have project code in your machine, then you use a Docker file to automatically generate a Docker image, and then you can instantiate one or more containers. This is, of course, something you do inside boot to Docker, or natively if you have a Linux machine. Then you can just send the containers to a Docker Hub or maybe to Quay.io, and then from there you can copy them into the staging server and production server. The environment will always be the same. This is the promise of Docker. So in this case, deployment is, in theory, vastly simplified. And of course, this is in theory because it's good for a very simple application. It becomes a bit more complex when you are trying to tackle real-world use cases. A Docker file is essentially instructions, commands that you want to execute to build a Docker image, but you want to do this automatically. This is an example of a Docker file. You take the Ubuntu as a base image, the latest one. You specify a maintainer. This is me. You can run specific commands. In this case, I'm updating my software, and then I'm installing NGINX, which is a web server, and then I can, echo something on the index file and expose port 80, and then I can build a new image with a specific tag, which is Simone Brunozzi, my name, /simple nginx image, and then the dot at the end is important. This assumes that your Docker file is in the same directory in which you issue the command, and then you can run, so you can launch a container based off of that image with those parameters on port 80 with the name nginx1 using that specific image and daemon off. One other thing that Docker, the company, is doing is providing orchestration services. Those are essentially three things: Docker Machine, which is a host that runs the Docker engine; Docker Swarm, which is a clustering service that allows you to just throw resources inside this pool, and it supports Zookeeper, etcd, or Consul; and Docker Compose, which is very much like AWS CloudFormation. It allows you to assemble an application, to specify rules on how an application works. They also are going to launch Docker Hub Enterprise, which allows you to have multi-container distributed applications behind your firewall. And of course, it can use public or private Docker repositories. Amazon, Microsoft, IBM already have endorsed Docker Hub Enterprise. It also provides you with high availability and scalability horizontally, and it should be available between end of Q2 and early Q3 2015, let's say July 2015 or maybe August. And there's also a trend of minimalist OS operating systems that are focused on running containers. CoreOS is probably the most well-known example, but also Atomic by Red Hat, Ubuntu Snappy, Rancher OS, or Nano Server by Microsoft. The main advantage is it's a smaller attack surface. It makes them more secure. The image size is much smaller, and they always allow you to have a transactional upgrade or rollback. So if you upgrade the machine and then the machine doesn't work, you can always roll back to the previous version of the machine, including the kernel and everything. And it's easy to do because the image size is very small, so it doesn't require too much extra space for this specific functionality. And those minimalist OSs are very important in the container ecosystem, or specifically for Docker. Some other Docker concepts: containers can have a name. It's essentially a valid DNS name, and that is very important for links, because one of the hardest things to do is to connect containers together, especially if they are on different hosts. Using links that can discover each other and then transfer information securely. So for example, you run a container called db, and then this is the first command you see here, and then you can run another container called web, which is linked to DB, and therefore those two containers can talk together now. A data volume, another important Docker concept, is a directory within one or more containers that bypasses the union file system, which is the file system used within Docker. The purpose is to separate code and data and then share data between containers through the volume. Those are some of the features of volumes. They are initialized when a container is created. They can be shared among containers. Changes to the volume are made directly, and it will not be included when you update an image. So essentially, data volumes persist even if the container itself is deleted. And a volume can also be accessed by another container even when a container is stopped. Another very important thing is that now there is an emerging trend of Docker as a service. Google, Amazon, through EC2 Container Service, Tatum, Orchard, StackDog, and a few others are offering Docker as a service. And this is essentially a way for you to host your Docker containers in the cloud without worrying too much about the details or about the underlying infrastructure. Now, how does Docker operates in the real world? Well, it depends. If you want to run Docker in a safe and robust way, then you need to have a few things done right. You need to have a secured private image repository. You need to already have orchestration enabled with zero downtime rollbacks. You should have sorted out how networking works between containers on multiple hosts. You need to manage logs, data, etc. You need to create images that properly handle init and logs, etc. So you can't just start using containers for a real-world use case right away. You need to just make sure that you are ready for it. Those are some of the use cases claimed by Docker. In all honesty, those are of course good names. At the same time, it's usually a small team within that specific company that uses Docker, not the entire company. So it's nice to see eBay on this list, but at the same time, it's only a few people within eBay that are using Docker in production for something real. Most of eBay doesn't use Docker yet, and the same is true for all the others. So there is some adoption, but it is not as big as we might think. There's also some misconceptions about Docker that we want to just diffuse. First, they tell you run just one process per container. However, it is far simpler if you manage Docker very much like you would manage a role-based virtual machine. You just build an app container, very similar to an app VM, and then with the other processes. If you instead want to have a process per container, it is very much like a nightmare to actually manage those containers properly and manage your applications properly. Even if you think you don't need a configuration management tool, you need an orchestration tool to provision, deploy, and manage your servers where Docker runs. So this is a very important misconception that we need to clarify. You might want to use Docker right now and you can't wait. However, you should have several things in place before you can run Docker and get the benefits that you think you're going to get. And those are some of the things. I'm not going to read the slide. You can just read them by yourself. Important point though, you might need to refactor your applications to be able to run on Docker well. If you're interested in learning more about it, look for 12-factor app or microservices. Another misconception is that only Docker or containers allow you to get those speed advantages. Well, there are many alternatives to achieve similar benefits, maybe not the same, but all those alternatives together provide certain types of benefits. Configuration management tools, cloud images, version pinning, version control deploys, packaged deploys, etc. All those things bring benefits, most of which Docker claims to bring as well. So Docker is not the only way to get those benefits to your infrastructure. What are the challenges with Docker then? One is definitely networking. It's very hard to connect across hosts. You can use service discovery. Swarm by Docker has been created especially for that. etcd by CoreOS is also built for the same reason. You can use some form of software-defined networking. Actually, socketplane.io has been recently acquired by Docker because they think it's very important. Lack of enterprise feature as well, another very important challenge. Those are all things that an enterprise will need and that Docker currently doesn't offer. In particular, admin tools for large deployments, auditing, logging, regulation, compliance. If you want Docker in the enterprise, you need those things. Security, of course, the mother of all problems. There's lack of encryption. Docker API endpoints might be security weak point. Containers can execute too many syscalls and therefore create issues in the host that where those containers are operating. It might access file systems. And as Dan Walsh, which is the creator of Security Enhanced Linux, put it very nicely, containers do not contain. So there's still a lot of challenges around security for containers. There's actually an interesting idea to monetize Docker. If you create an integrated security scanner that checks the package lists of each image and warns users when a vulnerability comes out, that will make images way more secure than what they are now. In fact, this is a diagram, and the source is below, that shows you that a lot of Docker images have known vulnerabilities, and we go to the 36 to 40% of those that have high priority vulnerabilities. Those are things that usually you need to fix within a day or two. So in general, the state of security in Docker is still pretty disappointing. So what does a real customer say about Docker? Let's hear from Aaron.io. They published a nice blog post. This is dated a few months back, so some of those concerns have actually been fixed, but still, they've launched a lot of containers. This is what I've learned by doing it. Good about Docker, easy to update and maintain images, good resource allocation, easy integration with Docker files. There's a growing community. Docker and CoreOS together are also very good. This is before CoreOS launched Rocket, so the relationship there might be different. Challenges, very limited backwards compatibility, limited tools, long deletion times, and some buggy issues like volumes not unmounting or memory limit switch, etc. So let's conclude now. I think that Docker is a very promising technology, and containers in general. They can be very good for specific use cases. If you look at web infrastructures, then it is very natural to think about Docker or Rocket to run that infrastructure. If you're talking about enterprise applications, not so much. There's a ton of buzz around Docker, but real use is still very limited. And of course, it is not as easy as depicted. And again, the community is now in a turbulent time. With Rocket, there is essentially a split. There are two main schools of thought about how containers should be done. And actually, what Rocket is doing is very interesting. I'm not going to cover it here, but it is something you should look for if you are interested in using containers in production. That's it for now. I hope that this was useful to give you a brief overview of what Linux containers are and what's the status of the technology right now. You can reach me on Twitter. I'm Simon, and thanks for watching.